Hey scholars, it's good to be back with you. And today it's time to start talking about Laplace transforms. Now Laplace transforms are the second of the integral transforms we've been talking about. The first of which was the Fourier transform. And you can see here it's got the same form that all integral transforms have. There's an initial function and a kernel function. And that's K-E-R-N-E-L. It's called a kernel function. Kind of like a kernel of corn, I guess. Different than the Army kernel. That's something completely different. So it's e to the minus st, where s is sigma plus I omega. So it's pretty obviously related to the Fourier transform. That term right there, which gets called a damping term a lot, if that goes to 0, what you've got is a Fourier transform. Now we use the Laplace transform almost exclusively for solving differential equations. And I'm getting a little ahead of myself here because we're doing differential equations next. But it seems to fit in with integral transform, so here we are. As far as I've ever seen in a book or experienced in my own engineering experience, I've never seen anybody present measured data in the S domain. You don't see plots much where you've got experimental data or measured data where the horizontal axis is S. It's always omega. So when you're looking at frequency domain, that's always Fourier transforms. And again, my experience has been that Laplace transforms are limited to solving differential equations. But if that's what you want to do, they're dang handy. I recommend. So let's back up a little bit and see what let's take this apart a little bit and see what lives inside of it. So I'm going to erase this real quick. And we're going to go back to the Euler relation, which is this. Now we developed this earlier, I guess I mentioned it earlier, that this is the Euler relation. Leonhard Euler discovered this. And the way he found it was to take the Maclaurin series expansion for e to the x and just substitute in ix instead of x. And what he realized he had was the expansion for cosine x plus I times the expansion for sine x. This is a very deep relationship. It underlies an awful lot of the mathematics that engineers and scientists use. It's under the hood there a lot of the time, even though if you don't see it. Now again, it's tempting to look at this and say, well, what's this really mean? As if there's some sort of physical significance behind it. I think that's the wrong question. This doesn't mean any more than this. This is a very useful relationship, but it's not correct to look at it and go think there's some sort of underlying physics behind it. There isn't. This is a mathematical relationship that's true. Let's use it. So the first thing we're going to do is substitute I omega t in. Okay, that's the kernel function for the Fourier transform. And we're going to get cosine omega t plus I sine omega t. Well, all right, that looks pretty good. We've used this a lot already. Well, what happens when we write e to the st? Well, let's see, that's e to the sigma plus I omega t. All right, well, that actually, we can break that down into a product. That's e to the sigma t times e to the I omega t. Well, that's a Fourier transform. That's the kernel for a Fourier transform. So it's e to the sigma t times this. There, I'll get out of your way so you can see that. So you get the exact same function, but now you've got it multiplied by this exponential term. Well, if damping is negative, it means energy is going away. So if damping is negative, this becomes a decaying exponential, which is handy for real-world vibrating systems, oscillating systems, where there's energy loss. Any vibrating system is going to lose energy, and you're going to see this exponential decay of a sinusoid over time. Well, that's what that looks like. There's one other property that makes this really handy. If you want to solve an initial value problem, a differential equation, a differential we'll call it time domain here, it's usually where you're starting from, becomes multiplication in the Laplace domain. And so that you can take a differential equation that's hard to solve, transform it into Laplace domain, work with it algebraically there, and then once you've got an answer there, transform it back into time domain. So if you think about how engineering mathematics works, how much of the time are we taking a problem we don't know how to solve, transforming it into an equivalent problem we do know how to solve it, and then transform the answer back into whatever domain we started with? We do that a lot. And that's basically the big idea behind Laplace transforms. I'm going to stop there because we're going to hit this again when I start talking about differential equations. So maybe we'll call this foreshadowing for all you English majors out there. With that in mind, let's go to my computer and dip our toes in the water and see what this looks like.